Okay, so we recently started talking about electron configurations and orbital notations. At the end of the first 6 weeks, which is now about 2 weeks ago, we had you had done a little mini project where you had to identify periodic table families, and you also had to identify trends. So all of that happens to be on this sheet here, which you should also have a copy of from class. One thing we've added since we've been talking about our orbital notations, electron configurations, is our S blocks, our P blocks, our D blocks, and our F blocks, as well as labeling it. So your S block is made up of groups 1 and 2. That S block also includes helium over here. Okay. Helium is part of noble gases because helium is already satisfied. It has 2 electrons, which is the number of electrons it needs to be satisfied. So that's why it's part of your noble gases as far as properties go. Remember, noble gases are inert, they don't really react, but it is part of your S block. Your P block, which is right here, is what we call our main group elements, and that's 13 through 18. So this is your P block. Your D block is your middle here, is your transition metals. And then your F block is your lanthanides and your actinides down here. It is very important that you have this on here. Like, this is going to be key for you for the next however many months, besides the fact that it's already color coded for you. It's got families already picked out. It's got information on here like number of valence electrons, what the charges are, everything else. This you're going to want to keep. And like I said, I had y'all put page numbers on here. This is going on page 25 in your notebook, all right? So I had you outline where your blocks are. You'll notice I outlined this one in blue. My P block are outlined in green. D block are outlined in orange. F block are outlined in purple. Then I went through and I also labeled it. So in your S block, the very first energy level, which is energy level 1, remember energy levels are your periods. So 1, 2, 3, 4, 5, 6, 7. In your first energy level, you can only have one subshell, and that's because of the fact that the first energy level can only hold 2 electrons. So all it is one S. So S starts with a 1. When you move to your second energy level, you can hold up to 8 electrons. So your second energy level is going to have a 2s, but that is also where your P level starts. So it starts at 2p. Okay, that's why your P block starts at 2p. When you get to um, your third energy level can hold a total of 18 electrons. So that's why you have a 3s, the 3p, and that is why your 3d, your D block, starts with 3, because the third energy level is the first level you can have 18 electrons. When you hit your fourth energy level and above, we're not really talking about going too much further than probably 6 for y'all, but when you hit your fourth energy level and above, you can have 32 up to 32 electrons on your orbitals. So that means you have your 4s, your 4p, so that's 8, your 4d, so that's another 10, so that's 18, and then your 4f level makes it a total of 32. So that's why it's numbered how it is numbered. So it's numbered 1s down to 7s, numbered 2p down to 6p, 3d down to 6d, and 4f down to 5f. The other thing to remember is how many electrons can be held in each of these sublevels. In your S sublevel, you can hold 2. Well, in your S block, you've got 2 electrons, right? So that's each one's an electron. In your P subshell, you can hold up to 6 electrons, and if you count, you've got 6 elements. In your D block, you can hold up to 10 electrons, and once again, if you count, you've got 10 elements. And in your F block, you've got 14 elements, and you can hold up to 14 electrons. So it's very important that you have this labeled as it is, okay? The periodic table that is in the classroom, once I get it fixed, it'll be perfect for y'all to use, but you will have already noticed if you've been in class looking at it at all that, hey, all this information as far as it being labeled is already on there. So that'll be there for you to use for tests and quizzes, but the important thing is you got to know how to use it. So this was one of the most important things we did. Next thing we did is we actually looked at notes. So these notes here that say electron configuration, these notes are going to end up going on page 26 in your notebook. All right. So they end up going on page 26 in your notebook. Okay, so this is on page 26. The first thing we have is it's asking us to define an atomic orbital. An atomic orbital is simply a region of space in which there is a high probability of finding the electron. So it's a region of space in which there's a high probability of finding the electron. Now this part down here, remember for mainstream chemistry, in other words, my every class period except for second period, you can cross this out. You don't need to worry about quantum numbers. For advanced chemistry, there's going to be a separate video for you to watch that'll go over that specifically. So that's electron configuration. All right. Other thing you needed to know is that there's 7 periods, and each of those corresponds to a principal quantum number, which just means what energy level are we on. So period 1 is energy level 1, so on and so forth. So you just copy this in. Okay. As you get to a higher period and a higher principal quantum number, the bigger the atomic orbital. So 7, atomic orbital 7 is really super huge. Okay, it's all this means. This table right here is very important. This contains information you have to know. So this quantum number, you don't need to worry about what the secondary quantum number is unless you're advanced chemistry. But like I said, there'll be a separate video. For mainstream chemistry, you just need to know you have the S, P, D, and F. These are called your subshells. Each of these subshells can hold so many electrons. The S subshell can hold 2, P subshell can hold 6, D subshell can hold 10, and F subshell can hold 14. So earlier, when I brought this over, remember I said in S, there's 2 elements, 2 electrons. P, there's 6 elements, 6 electrons. D, 10 elements, 10 electrons. And F, 14 elements, 14 electrons. Okay, that's where I was bringing that in earlier. You need to know their shape. So S is shaped like a sphere. P is shaped like a dumbbell. And then D we say is shaped like a clover. Then F we just call that complex. All right. Then every class period except second period could also cross this chart out. Okay. So when it comes to reading electron configuration, so this is one thing you have written here. So 1s2, 2s2, 2p2. Okay, this is an example that was given on the PowerPoint. All right, so it's already telling you it's for carbon, but let's pretend you didn't know what it was for. Let's just pretend you were given this configuration. I asked you to figure it out. One of the ways you can figure it out is by saying, okay, what is my last part of this configuration? So what's my last number, letter, and superscript or exponent? 2p2. So I'm going to go to my periodic table, which is nice and labeled, or you look at the one in the room. I find 2p. I want 2p2. 1, 2. There's carbon. So the exponent is how many electrons there are. Remember that each of these elements corresponds to an electron. So because it's 2p2, row 2p, 1, 2, it's carbon. That's one way you can identify an element based off of the configuration. The other way is add up your exponents. So add exponents together, and that equals your atomic number. Add your exponents together, and that equals your atomic number. So if I add my exponents, 2, 4, 6, and then I go to the periodic table and I say, okay, I want atomic number 6. There it is. There's carbon. So that's the other way you can identify. So identifying an element based off of it is pretty simple. Writing it is actually pretty simple too, but you just have to think about it. So what this part here is showing you, this is called a fill diagram, and this is how you fill it. So you fill it, you start at 1s, and what it's asking you to do is asking you to do this. So you start at 1s. When you finish filling 1s, then you go to 2s. You go through 2s. When you finish 2s, you come back around. Then you're going to fill 2p and then 3s. If you fill all 3s, come back around. You're going to fill 3p, then 4s. If you fill all that, and you come around, you're going to fill 3d, and then 4p, and then 5s. If you fill all that, you come back around, you're going to fill 4d, 5p, and 6s. If you do all that, come back around, then you're going to go 4f, 5d, 6p, 7s, and if you happen to fill all that, come all the way back around, you'll fill through 5f, 6d, 7p. So this is called a fill diagram. This is how you fill it in. So one way of doing this, so now I'm going to use a separate sheet of paper, and we're going to take magnesium. Okay, so I'm going to do magnesium as an example here. You don't have to do this anywhere on here unless you want to. If you want to, put it on white space. But let's check out magnesium. If you look at your periodic table, which is right here, okay, magnesium has an atomic number of 12. Remember that the atomic number is a number of protons, which is going to be the same number of electrons unless we're talking about an ion. So therefore, when I write my configuration, I have to put 12 electrons. Where do we start? So you can use this way if you happen to memorize this way. I start at 1s. According to this, s can hold 2 electrons. So that means I started with 12, now I have 10 left, right? So this is my number of electrons here. Okay. After I get through 1s, because I'm not done, that doesn't equal 12, I circle around and I'm going to go to 2s. S can hold 2 electrons, so I put a 2. So I just used another 2 electrons, so that leaves me with 8. So I'm still not done. So after 2s, my diagram says, okay, you go to 2p. P can hold 6 electrons, so I'm going to put a 6. 8 minus 6 leaves me 2. So I'm still not done. So after 2p comes 3s. 3s can hold up to 2 electrons, which is how many I have left. So there's my electron configuration for magnesium if I do it this way. All right, and you can double check. 2 plus 6 is 8, plus the 4 is 12. Okay, so that's using the fill diagram. Now you're not going to be, you might have this on a test, like I might have this part, but it won't have the rings on it. Okay, you'll have to understand what this means. So this is a fill diagram. How I suggest you do it, however, is just by looking at your periodic table. So if we do this by looking at our periodic table, anytime I ask you to give me the electron configuration, so in this case I said magnesium, right? You put your finger on magnesium. This is where you're going to stop. You have to treat this like a map. Just like with a map, you always start at your starting point. Our starting point is always hydrogen, right? So we want to go to magnesium. I start at hydrogen. That means I'm stopping here. That means I got to go through all of this. So I just start simply listing. So I say, okay, I got to go through 1s, I got to go through 2s, I got to go through 2p. See how I'm doing this? I got to go through 2p, and I got to go through 3s. Okay, now I fill in my exponents. So everything that came before 3s, I had to go all the way through it. So I know I need to fill those up. When I look at 3s, 3s1, 3s2, I'm done. Okay, that's magnesium. So that's how you do that part. Now on this page here, which this one's going on page 27, this one here, if you flip over, you've got some practice. Okay, so where you're going to be practicing is up here. All right, we did all this in class. So I'm going to do an example back here. I'll go ahead and write all of these. So I'm simply getting this from the periodic table. So, but I want to try a hard one. So let's go ahead and do lead. Okay. So lead's where I'm going. So I'm going to keep this here. Move that out of the way. So I'm going to keep this over here where hopefully you can see it. And here is my periodic table. Okay. Lead is right here. We always, always, always start at hydrogen. So I know I'm stopping at 6p. I know I have to go through everything else. So I know I have to go through 1s. I have to go through 2s. Have to go through 2p. Have to go through 3s. Have to go through 3p. Have to go through 4s. Have to go through 3d. I have to go through 4p. I have to go through 5s because I'm still not there yet. I have to go through 4d. I have to go through 5p. I have to go through 6s. Now, notice how you have this chunk that comes out, right? So don't forget to go down. You can't go from 56 to 71. So you're going to go down. So this is 4f. I have to go through 4f because I'm still not here at lead. Then I come back up. After 4f, I have to go through 5d. And I know I have to go to 6p. 6p is where I stop in lead. So here's my 6p, 1, 2. So it's 6p2. So on here, when I finish writing this, I need to go back and put all the exponents. This is where I stopped. So now, every S, I'm going to put a 2 because S's can hold 2 electrons. Every P, I'm going to put a 6 because P subshells can hold 6 electrons. So that's a 2, that's a 6, that's a 2. When I have a D subshell, I'm going to put 10 because D subshells can hold 10 electrons. There's a P, so that's 6, S is 2, D is 10, P is 6, S is 2. When I hit F, F subshells can hold 14. There's a D, so that's 10, and then 6p2 is when I ended. That is how you do electron configurations. It's simply reading the map. So like I said, the easiest way for me and the easiest way I think would be for you is put your finger where you're going and just start writing what you pass through and then go back and fill in. So remember, it's just like reading a book, left to right, top to bottom. Okay, so that was just plain old electron configuration. Now we're going to talk about noble gas configuration. So let's go back to this one here. Example electron configuration for noble gas configuration for bromine. Here's how simple noble gas configuration is. All you do to do noble gas configuration, find the element we're looking for. In this case, we're looking for bromine. You're going to go up a row all the way over to your noble gases. This is your noble gas. You put that noble gas in brackets. So argon goes in brackets. Now, I just have to finish out what comes after argon. So I'm going all the way to bromine. So I've stopped here, but I'm going to here. So now I have to go through 4s, I have to go through 3d, and I have to go through 4p. So it's like I just got done saying, so I'll move that there, move this down here. So bromine's here. I have to go through 4s, have to go through 3d. 4p is where I'm going to stop. That's 4p, 1, 2, 3, 4, 5. And then just fill in your other exponents. Remember, S can hold 2, D can hold 10. And you're done. That's noble gas configuration. That is to keep us from writing forever and a day. You know, this one here, this lead here was 82 electrons. If I wanted you to do all the way to number 112, that would be a lot more writing. So if we were to take a look at lead on here, and we said, okay, here's lead, right? If I want to do noble gas configuration with that, I would go up all the way over to the right, and that would be xenon. Xenon stops at 5p. 1, 2, 3, 4, 5, 6. Xenon stops at 5p6. So if I found lead here, here's 5p6. All of that right there would be contained in the brackets if I would have just simply put xe. And all you would have had to write was this little part out here. That's what noble gas configuration allows you to do. All right. So beryllium and fluorine. So we'll do beryllium first. Beryllium, upper row all the way over. So its noble gas is helium. So He goes in brackets. Then I have to finish it out. So we want beryllium. So after helium comes 2s, and that's where I'm going to stop. Beryllium is 2s2. Fluorine. Here's fluorine. Go up one all the way over. Oh, it's also helium. I need to finish it out, so I have to go through 2s. I have to go to 2p. 2p is where I'm stopping, and I'm stopping at 1, 2, 3, 4, 5. So 2p, 5. And that was a 2s, so that's got to be a 2. Platinum. Here we go. Platinum's right here. Go up a row all the way over. So platinum's noble gas is xenon. So I'm going to put xenon in brackets. And then I have to finish out the platinum. So after xenon comes 6s. Remember that after 6s, you got to drop down. So I have to go through 4f. Okay, so you have that so far. Come back up, 5d. Okay, that's where my PT is located. My platinum is located. So it's located in 5d. And it's located at 5d. 1, 2, 3, 4, 5, 6, 7, 8. And I just fill in the rest. Remember, S can hold 2, F can hold 14. You're done. That's noble gas configuration. All right, so it's simply shorthand. You just find the noble gas by going up one row from the element you're looking for, all the way over to the right, and then finish it out. Last type of configuration we have is called electron configuration for ions. So in this case, for carbon. Okay, I'm going to go ahead and write what carbon normally is, which we already have up here. Carbon is normally 1s2, 2s2, 2p2. But what happens whenever you form ions is, remember, you only care about your valence electrons. Valence electrons are the ones that are out here on your outermost shell. So these are our valence electrons. This happens to be a +2 charge. Remember, it's the number of electrons that change. So if our ion is positive, we have to lose electrons because we have to lose the negativity. So we're going to lose 2 electrons. Where do we lose those 2 electrons from? We lose them from our valence shell. So that means both of those electrons go away, so 2p doesn't even exist. So electron configuration for carbon with the +2 is 1s2, 2s2. Which if you look on your periodic table, if I ask you to identify what is this element, and you say, okay, ends at 2s2, here's 2s, 2s2, it's beryllium. All right. Or remember, 2 + 2, that's 4, atomic number 4, that's beryllium. Okay. And your ions, whenever you're doing this for ions, you are going to make the electron configuration for a completely different element. That's because you are adding and losing electrons. So on your practice problems here, we have sodium with the +1, calcium with the +2, oxygen with the -2, and fluorine with a -1. So that's just a negative, that's just a positive. It's understood to be +1 and -1. So looking at sodium. Sodium, if you take a look at your periodic table right here, ends at 3s1. So I have to go 1s2, 2s2, 2p6, 3s1. This is a +1 charge, so I lose an electron, and you lose that from your valence shell. All right. Calcium. Look at your periodic table. Calcium ends at 4s2. So I write this. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium has a +2 charge, so I lose 2 electrons from my valence shell, so that's that one. So I just cross that out. Okay. Oxygen. Oxygen ends at 2p4. So 1s2, 2s2, 2p4. This happens to have a -2 charge. Because it's negative, we're going to add electrons. So it's -2, so we're going to add 2. We add those 2 to our outside shell, which is this one. So that 4 becomes a 6. Fluorine has a -1 charge. Fluorine stops at 2p5. So 1s2, 2s2, 2p5. It has a -1 charge. So we're gaining 1 electron. We gain that 1 electron in our outside shell, so that 5 becomes a 6. Something I want to point out to you is now these are your valence shells. So the ones I underline are your valence shells. If you take a look at what I underline, all of them have an S and a P, and they're all full. So they all have 8 electrons. Remember, your noble gases have 8 valence electrons. This is why they don't react, because they're already satisfied. The only exception, of course, is helium. Helium can only have 2. Okay, but everything else has 8. Helium satisfied with 2, everything else is satisfied with 8. So they already have a full valence shell. They don't need to react. They don't need to become ions to be happy. And that's what you're doing when you form an ion. When you form an ion, you're adding or gaining electrons so that you become more like a noble gas. So that is your ion electron configuration. Okay, last thing we had to look at is something called an orbital diagram. So you're going to flip this page. So it says define orbital diagram. All an orbital diagram is an electron configuration picture. That's all it is. It's taking the electron configuration you've already done and making it into a picture. It also asks you to draw an arrow to show how the energy increases. So energy increases from bottom to top. It increases as you fill in the higher levels. What you need to know, so you see how you have boxes drawn here? These are orbitals for each of your subshells, okay? Because when you make a diagram, it's going to look like this. You're going to have these little orbitals and you're going to show electrons in them. So remember, you've got your subshells S, P, D, and F. So I just made a quick chart. Okay. Remember that in your S subshell, you can hold 2 electrons. P subshells, you can hold 6. D subshells, you can hold 10. And F subshells, you can hold 14. Every one of these orbitals that you have hold 2 electrons. So if every orbital can hold 2 electrons, that means in your S subshell you have 1 orbital. P subshell you have 3. D subshell you have 5. And F subshell you have 7. This is the part you have to know. So when you see an example orbital diagram, which is right down here, the electrons spin opposite of each other, and we usually depict the electron spins using arrows that point either up or down. So this is the orbital diagram for carbon. So for carbon, we need a 1s, a 2s, and a 2p. So 1s, so we're going to draw one orbital for 1s. Our 2s, so it's also an s, so we need one orbital for 2s. Then we need also a 2p. Well, p orbitals can hold, or p subshells can have 3 orbitals. So I got to draw 3 orbitals for 2p. Okay, so that's how they get the number of boxes they need. Then you just go through and you fill it up. And you say, okay, carbon stops at 2p2. So 1, 2, and I'll explain to you in just a second why they're spaced and not doubled. And then everything else is filled up. Okay, so that's your orbital diagram. There's 3 rules you have to follow when it comes to filling in orbital diagrams. First one, called Aufbau principle, says each electron occupies the lowest energy orbital. This just means you start at the beginning. Okay. So you have to fill the lower orbitals before you move on. So in other words, everything up to 4s has to be filled completely before I can get to 3d. That's what that's talking about. Pauli exclusion principle says that only 2 electrons can fit into a single orbital. This is your opposite spin. That's your opposite spin. So that means in an orbital, so in one single orbital, that means one of these boxes, you have an up arrow and you have a down arrow. They have to be opposite spins. Hund's rule states that electrons go into different orbitals in the same sublevel before doubling up inside orbitals. This is what we call the bus seat rule. So bus seat rule. I don't know about you, but when I ride a school bus, at least when I used to, when I was younger, I always got on the bus and I looked for a spot by myself first before sitting with anyone. And that's what this is talking about. This is talking about how electrons have to sit 1 electron per orbital before they double up. That's why over here, remember, P subshells has 3 orbitals, but I only need to put 2 electrons there. So I have to set each one individually before it doubles up. So that's why it's like that. Okay, so let's take a look at some examples. The way I suggest you do this, if I'm asking you this and I happen to be nice and I have these boxes for you already, all you do is you say, okay, I want hydrogen. Hydrogen stops at 1s1. So here's 1s. I'm going to put 1 electron. Done. Helium stops at 1s2. Here's 1s, 1s1, 1s2. Lithium stops at 2s1. So I'm going to find 2s. I need to put 1 arrow. Off-bow says everything below it has to be filled first. So I'm going to go ahead and fill that in as well. Sodium. Sodium stops at 3s1. So here's 3s. There we are. Everything before that has to be filled up. That means everything before this has 2 electrons. Oxygen stops at 2p4. So here's 2p. There's 3 bus seats because there's 3 orbitals. I need to put 4 electrons there. So 1, 2, 3, 4. Because you have to put them individually before you double up. And then everything before that should already be filled. Chromium, if I look at chromium, chromium's right here, 3d4. So here's 3d. There's 5 orbitals in 3d. I only have to put 4 electrons. So 1, 2, 3, 4. And then everything before it has to be filled. Okay. So that's doing orbital notation. It is simply taking your electron configuration because I can get that from this. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Because I can get my orbital notation, or I can get my electron configuration from the orbital notation. All right. So this is what we've done in a nutshell. So for my regular students, this is what you need to know. For my advanced students, I'm going to have another video that's going over the principal or the quantum numbers for you and what you need to know with those.